Welcome to Maths with EJD. We're still talking about real analysis, and this video is about power series and elementary functions. In the last video, we had looked at sequences and series of functions, comparing pointwise and uniform convergence, right? So, power series and elementary functions. So, let's look at some of the core concepts here. First of all, we have power series and radius of convergence. Okay. So of course, like we already know, a power series about x naught. The other time the center was A, right? So when we say about x naught or about A, it means that x naught or A is the center. In this case, it's x naught. So a power series about x naught is summation from n equals 0 to infinity of A sub n into x minus x naught raised to power n. So its radius of convergence R, which belongs to the closed interval 0, infinity, is characterized. So it means that the radius of convergence can take values from 0 all the way to infinity. And it is characterized by the root or ratio tests, so that 1 over R is the limit of the supremum as n approaches infinity, or the nth root of the absolute value of an, like this. That's it's the same thing we saw the other time when we are talking about absolute value of Cn raised by 1 over n. It's exactly the same thing in the previous video. Or we can say R is limit as n approaches infinity for the absolute value of an over n plus 1 if the latter limit exists. So if the limit exists, this is what we do in that situation. Okay? So this series converges absolutely for absolute value of x minus x naught less than R. Or like previously we are saying x minus a like that. So whether it's x naught or it's still talking about the same thing. And the diverges for absolute value of x minus x naught greater than R. And the boundary x minus x naught equals R must be checked separately, just like what we talked about in the other situation. And in the other video, I mean, the video before this. Okay, so uniform convergence on compactor inside a disk. So if K is a subset of the open interval x naught minus r, x naught plus r is compact, there is r less than K, big R, which with K, which is a subset of a closed interval x naught minus that small r plus, x naught plus that small r. And since summation from n equals 0 to infinity of an into x minus x naught n is dominated on K by summation from n equals 0 to infinity of an multiplied by Rn like that. The Weierstrass test gives uniform convergence on K, and the consequences include that limits and termwise integration are justified on compactor. If each partial sum is continuous, then the limit is also continuous. If each partial sum is differentiable and derivatives converge uniformly on compactor, the limit is differentiable with derivative. The limit is differentiable with derivative of the uniform limit, I think. So then termwise, we have termwise differentiation and integration of power series now. So if we have the absolute value of x minus x naught less than R, the function f of x equals summation from n equals 0 to infinity of an into x minus x naught and raised power n is infinitely differentiable, and f of x is equal to summation from n equals 1 to infinity of n into an into x minus x naught raised by n minus 1. And the integration is integral f of x dx. I think this is the kind of thing we had in the previous video also. So we have the arbitrary constant c plus summation from n equals 0 to infinity of an over n plus 1 into x minus x naught raised by n plus 1. So the key factor is that the derivative and antiderivative series have the same radius of convergence R. So it's exactly like what we discussed the other time. So we are reiterating some of the concepts previously. So, where we might have some difference now is when we talk about, okay, I mean, we've seen some of these things also in the previous video, but let's see how it goes. So we talk about some elementary functions via power series. So first of all, we start with exponential function. So if we define the exponential function x to be summation from n equals 0 to infinity of x raised by n over n factorial with radius of convergence infinity, then these are the following properties. Exponent prime of x is exponent of x. So if you differentiate an exponential function, you end up getting fundamentally the same function. Then at x, if you evaluate at 0, of course, you're going to have 1 because you have x raised power something. Then, or it's something raised power x, right? So like that. So exponents at 0, e raised power 0, of course. So e raised power 0 is 1. So exponent of x is always greater than 0, no matter what x is. And exponent is strictly increasing. It is strictly increasing. So as x increases, it also increases, right? Then you have the Cauchy product identity. So the exponent of x plus y is equal to exponent of x multiplied by exponent of y. That's the Cauchy product identity. Then for complex numbers, e raised power I theta is equal to cos theta plus I sin theta. So that's the Euler's formula, which I have a playlist on complex analysis, which you may want to see. That we talked about that there. And talking about trigonometric functions now, we're talking about some elementary functions. We've talked about the exponential functions. So here, we're talking about the trigonometric function, right? So you have sine x equals summation from n equals 0 to infinity of minus 1 raised power n all over 2n plus 1 factorial x raised power 2n plus 1. And then you have cos of x is summation from n equals 0 to infinity minus 1 raised power n all over 2n factorial x raised power 2n. The radius of convergence again here is undefined, right? So the consequences include that the derivative of sine x is cos x, derivative of cos x is minus sine x, right? So if you differentiate sine x, differentiate this now, you are going to get exactly cos x. But then if you differentiate cos x, you're going to get negative of this one, like that. So using series multiplication and uniqueness of coefficients, we see that sine squared x plus cos squared x is 1. I have a playlist on trigonometry, and as we amply established this, so I think I was able to prove this using Pythagoras theorem, for instance, that sine squared x plus cos squared x is 1. And then we have other identities that arise from this idea, right? Then, so far, talking about some elementary functions, we talked about exponential, trigonometric. Now let's talk about logarithm, about 0. So for x lying between -1 and 1, this is what this means. For absolute value of x less than 1, then the log of 1 plus x equals summation from n equals 1 to infinity of -1 raised by n minus 1, x raised by n over n, and the radius of convergence is 1. So at the boundary now, we see that x is equal to 1. That converges to log 2 for all, and it's alternating harmonic. Then for x equals -1, it diverges for harmonic series now. So we have other classical series. So we've seen exponential, we've seen trigonometric, we've seen logarithmic series. What about other classical series like binomial? So for binomial, we have for absolute value of x less than 1, all right? 1 plus x raised to power alpha is equal to summation from n equals 0 to infinity of alpha combination n. So alpha choose n, x raised to power n. So alpha combination n on n, of course, is alpha into alpha minus 1 into alpha minus 2 all the way to alpha minus n plus 1. So multiplying all of that divided by n factorial. And then we have for arctangent. So for arctangent, we have arctan x is summation from n equals 0 to infinity minus 1 raised power n, x raised power 2n plus 1 over 2n plus 1. The radius of convergence is 1. So at x equals plus or minus 1, it converges to plus or minus pi over 4 in that case, right? So we have proofs of key theorems now. Proofs of key theorems. First of all, we have the uniqueness of power series. Uniqueness of power series coefficients. So if two power series agree on the neighborhood of x naught, that is summation from n equals 0 to infinity of an into x minus x naught raised power n is equal to summation from n equals 0 to infinity b sub n into x minus x naught raised power n, then we can say that an equals equal to bn, right? Because the power series agree on neighborhood of x naught. So you can see everything is like that. So an is equal to bn for all n. So we can prove that via derivatives at the center. So we say let f of x be summation from an, summation of an into x minus x naught raised power n, and then g of x is summation from bn into x minus x naught raised power n. So on the interval x minus x naught, which is less than r, on the absolute value of x minus x naught less than r, all derivatives exist. And then we see that the nth derivative of f of x naught, the nth derivative of f evaluated at x naught will give us n factorial a sub n. Then the nth derivative of the function g evaluated at x naught will give us n factorial b sub n. So if f is equal to g, then on a neighborhood, then we say that f n of x naught is equal to g n of x naught for all n. Hence, an is equal to bn. And the equivalence of that is that if a power series is identically zero near x naught, then all coefficients will vanish. All coefficients vanish in that situation. Okay. So we have time-wise differentiation and radius preservation. Time-wise differentiation and radius preservation. So let f of x be summation. This is a power series, of course. Summation an into x naught raised by n, where r is the radius of convergence. So for any small r less than the radius of convergence, big R, on the absolute value of x minus x naught less than or equal to r, the differentiated series would be summation from n equals 1 to infinity. Of course, when you differentiate this now, you have n into x minus x naught raised by n minus 1, and it is dominated, that is, I think it seems to converge towards this summation from n equals 1 to infinity of n into absolute value of an, then r raised by n minus 1, which converges. Hence, the derivative series converges uniformly on compactor inside R, proving f is differentiable with f prime of x equals summation from n equals 1 to infinity of n into x minus x naught raised by n minus 1. Thus, the derivative and antiderivative series have the same radius of convergence R. We've said this several times. Okay. So let's talk about the third one, the exponential Cauchy functional identity. The exponential Cauchy functional identity. So the claim here is that for all real x comma y, the exponent x plus y is exponent x multiplied by exponent y. So the proof is we use the Cauchy product. Since the series converge absolutely, so we have exponent x times exponent y. That's summation from summation over n greater than or equal to 0 for x raised by n factorial into summation from m greater than or equal to 0 for y raised by m over m factorial. That is equal to summation from k equals 0 to infinity into summation n equals 0 to k all over, multiplied by 1 over n factorial into k minus n factorial, x raised by n, y raised by k minus n. So by the binomial identity now, we can say that summation from n equals 0 to k all for 1 over n factorial into k minus n factorial is simply the same thing as 1 over k factorial, right? So we can say that exponent x exponent y is the same thing as summation from k equals 0 to infinity of x plus y raised by k all over k factorial, and that is the same thing as exponent x plus y. So the alternative approach is you can fix y and define f of x, which is exponent minus x exponent x plus y, then f prime of x is equal to 0, and f of 0 is exponent y, hence f of x is exponent y also. And then we talk about Taylor polynomials and error bounds. Okay, Taylor's theorem with Lagrange remainder. So if f belongs to an n plus 1 differentiable, c raised by n plus 1 is telling us that the function is n plus 1 differentiable, like it can be differentiated n plus 1 times over the interval, closed interval AB. Then for x near x naught, we can say that f of x is equal to summation from k equals 0 to infinity to n, then f k x naught over k factorial, x minus x naught k plus rn plus 1x, with the remainder r n plus 1 of x equals f into n plus 1 psi all over n plus 1 factorial x minus x naught n plus 1 for some psi between x and x naught. So if the absolute value of f n plus 1 of t is less than or equal to m on the interval, then we can say that the absolute value of rn plus 1 of x is less than or equal to m over n plus 1 factorial into absolute value of x minus x naught raised by n plus 1. Then we have some useful specializations, right? So we have exponential about 0. So since the absolute value of e raised power psi is less than or equal to e raised power absolute value of x for psi between 0 and x, we can say that the absolute value of e raised power x minus summation from k equals 0 to infinity of x raised power k over k factorial is less than or equal to e raised power absolute value of x all over n plus 1 factorial, absolute value of x raised power n plus 1. And then we have alternating series, e.g. log 1 plus x for x in minus 1 to 1, arctan x for x in minus 1. This is half open, half closed interval, and this is fully closed interval. So if term decrease to 0 in absolute value, then the truncation error satisfies that absolute value of Rn is less than or equal to first omitted term. So like if you have if you have Taylor series for something like e raised power x, you shown that that's like 1 plus uh x 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So if you stop at x plus x for over 4 factorial, so the error will be in terms of the error will be of order 5 upwards like that. So you have worked examples here. So for these worked examples, example A, approximating e raised power 0.5 with error target. So we want R absolute value of Rn plus 1 into 0.5 to be less than 10 raised power minus 6 using the Lagrange bound. So we have an error target. So we expand it like this. E raised power 0.5 minus summation from k equals 0 to n, 0.5 raised power k over k factorial less than or equal to e raised power 0.5 by n plus 1 factorial into 0.5 raised power n plus 1. So since e raised power 0.5 is approximately 1.649. Of course, if you punch that on your calculator, that's what you get. So for n equals 5, you see the bound will be 1.649 divided by 5 factorial, which is 720. Yes, 720. 5 factorial is 720, I think. Yeah. Now, oh, is this 6 factorial now? Oh, yeah. If 5, n is 5, so we have 5 plus 1. So that's 6 factorial. Yeah, 6 factorial is 720. I was wondering. So, and then multiplied by 0.5 raised power, that's 6. So that's approximately 5.7 times 10 raised power minus 5. So this doesn't quite reach there. So for n equals 8, we have the bound 1.649. That's for e raised power 0.5 all over 9 factorial. 9 factorial is 362,880 multiplied by 0.5 raised power 9. And that's approximately 1.3 times 10 raised power minus 7, right? So we see here that thus only n now. N is equal to 8. That's what guarantees that the error is less than 10 raised power minus 6. Okay, so it's more like some trial and error. So if you try 6 and 7, you discover that you don't still have that 10 raised power minus 6 guaranteed. But when we have 10 raised power minus 7 like this, then we surely know that's smaller than 10 raised power minus 6. So the approximation can now be, so it means you can do the expansion up to 8. So e raised power minus 5 will now be 1 plus 1 over 2 plus 0. I mean, this is 0.5, right? So it's more like you have 0.5 raised power 0 plus 0.5 raised power 1 plus 0.5 raised power 2 over 2 plus all that up to 0.5 over 8. 0.5 raised power 8 over 8 factorial. And that's actually approximately 1.6487213 because of the error that is required, right? So the true value is now given here. So we have, of course, that's when you punch calculator, that's what the true value is about. So for example, B now, we want to do log 1.2 via alternating series. Okay, so we want to apply all those series things now. So for x equals 0.2, so we have log 1.2, okay, and that is equal to summation from n equals 1 to infinity, minus 1 raised by n minus 1, 0.2 raised by n over n factorial. So that 0.2. So the alternative remainder estimate gives absolute value of Rn to be less than or equal to 0.2 n plus 1 all over n plus 1. So we need 0.2 n plus 1 over n plus 1 to be less than or equal to 10 raised per minus 4. Okay, so for n equals 4, now you have, for n equals 4, you have 0.2 raised per 5 over 5, and that is 6.4 times 10 raised per minus 4, minus 5, which is less than or equal to 10 raised per minus 4, like that. Okay, so 4 terms. So that tells us that 4 terms should suffice. That means that log 1.2 is approximately 0.2 minus 0.2 squared over 2 plus 0.2 cubed over 3 minus 0.2 raised per 4 over 4. So you know it's alternating series. And that's approximately 0.1822321, right? Because this is what the series actually gives on its own. So the error now is less than or equal to 6.4 times 10 raised per minus 5. And the true value is 0.182 3215568, like that. So how about sine 0.3 with guaranteed bound, right? Sine 0.3 with guaranteed bound. So this example C now. So use the Maclaurin polynomial of degree 5 here. So we have sine x. In fact, this is even yeah, this is Maclaurin. Yeah, this is Maclaurin, yeah, because Taylor talks about the center. So Maclaurin just assumes the center of zero, right? So sine x is x minus x cubed over 3 factorial plus x5 over 5 factorial. So for x equals 0.3, the next term is bounded by absolute value of x raised power 7 over 7 factorial. That is equal to 0.3 raised power 7 over 5040. 7 factorial is 5040. And that's approximately 2.1 times 10 raised power minus 6. Okay. So if you compute 0.3 minus 0.3 raised power 3 over 6 plus 0.3 raised power 5 over 120, that's approximately 0.2955520. Right? So true value is sine 0.3 is approximately 0.2955. 202067. I mean, if you use some computer, you punch a calculator. But of course, I mean, this is better done if you have an error you are working towards. Okay. So you want to know the number of terms I should use. Then we have proof sketches of exponential properties. So we have the derivative property from the series definition. We know that exponent of x is summation from n equals 0 to infinity of xn over n factorial. And if you differentiate term by term, we have d dx of exponent of x to be summation from n equals 1 to infinity of n into nx into n minus 1 over n factorial. I mean, that's the whole basic idea of differentiation. And if you do look at that now, this is just like so if you shift it, this is n equals 1. If you shift it by one step backwards, you end up with the same summation from n equals 0 to infinity, n factorial x raised power n, and you have your exponential of x back again. So those who say that the derivative of exponent of x is the same thing as exponent of x, and exponent evaluated at 0 is equal to 1, basically, because of course x raised power 0 is 1, 0 factorial is also 1, so everything is 1. That's for derivative property. Then we have addition law. For addition law now, as shown earlier via the Cauchy product, exponent of x plus y is the same thing as exponent of x multiplied by exponent of y. Alternatively, you can fix y and define f of x equals e raised power minus x raised power x plus y. Then f prime of x now, we differentiate f prime of x will be 0 and f of 0 is e raised power y. So f of x is e raised power y. Hence, e raised power x plus y is e raised power x e raised power y, like that. Then we have positivity and monotonicity. So since the derivative of exponent of x is exponent of x, and that is always greater than 0 because it's an increasing function. For all real x, the exponential function is strictly increasing, right? So also exponent evaluated at 0 is 1, and that is also greater than 0. And continuity implies that exponent of x is greater than 0 for all x in the real number line. So then you have uniqueness characterization. Suppose f is differentiable, satisfies f prime equals f, and f of 0 is 1. By the uniqueness of solutions to first ODEs, f of x automatically would have to be exponent of x. That means if you differentiate any function and you end up getting the same function you started with, and then you now evaluate that function at 0 and you get 1, then it means that it has to be an exponential function. That is the idea of uniqueness characterization. Equivalently, expanding f in the Maclaurin series gives f of x equals summation from n equals 0 to infinity. The nth derivative of the function evaluated at 0 over n factorial xn ends up giving us a summation from n equals 0 to infinity xn over n factorial. If that happens, automatically f of x is an exponential function because the end result shows us that summation from n equals 0 to infinity of x raised to n over n factorial. That's an exponential function like that. So we have some practice problems that you want to try your hands on and with some guidance that can help. So first of all, we have radius and boundary. So you want to find the radius of convergence for summation from n greater than or equal to 1 for x minus 2 raised by 3n all over n 3n. So B, determine convergence on the boundary. Okay. The hint is use the root test on this. So you have x minus 2 raised by 3 over n raised by n times 3 raised by n, raised by 1 over n. And that's approximately x minus 2 raised by 3 over 3. On the boundary, use Cauchy condensation and comparison with summation 1 over n, like that. So we want to try that out. The uniform convergence on compactor. So you want to prove that summation from over n greater than or equal to 0 of x over 2 raised by n over n factorial converges uniformly on minus 1 to 1. And the hint is watch out that it is dominated by 1 over 2 raised power n over n factorial, and apply the Weierstrass M test, because that's surely bounded like that. Okay, because as n increases, that approaches 0 for sure. That's why we say it's bounded. So we have termwise differentiation. Okay, so um if you let f of x be summation over n greater than or equal to 0 for x minus 1 raised power 2n plus 1 all over 2n plus 1 times 2 raised power n. You want to find r, you want to differentiate termwise to find f prime of x. You want to show r is the same for f and f prime. I mean, we've established that a lot, that the radius of convergence for the function and its derivative is the same. Okay, the hint is view coefficients as a 2n plus 1, which is 1 over 2n plus 1 multiplied by 2 raised power n, or then others 0. So you can then use root test, that absolute value of a sub 2n plus 1 raised power 1 over 2n plus 1. So that can help. Then you have uniqueness of coefficients. Suppose summation for over n greater than or equal to 0 of an x raised power n is similar to 0 for the absolute value of x less than r, then show that an is equal to 0 for all n. So hint, differentiate n times and evaluate at 0. So there you see uniqueness of coefficients. So we go to 7.5, exponential addition law via ODE. So in this case, you define f of x, which is e raised power minus x, e raised power x plus y, show that f prime of x is equal to 0, and conclude that e raised power x plus y is equal to e raised power x, e raised power y. Hence, you can use the product or chain rules and initiate value f of 0 equals e raised power y. Then you have Taylor approximation targets. So here you want to find the minimal n, so that the Maclaurin polynomial of e raised power x approximates e with 10 raised power minus 6. Then approximate arctan half by truncating its alternating series and bound the error by the first omitted term. Hint, use Lagrange remainder for a with m equals a for b, the alternating series bound. So that's how to go about that. Then 7.7, you have logarithmic via geometric series. So for absolute value of x less than 1, justify that log 1 plus x is equal to integral from 0 to x, 1 over 1 plus t dt is equal to integral from 0 to x, summation n greater than or equal to 0 minus t raised power n dt equals summation n greater than or equal to 1 minus 1 raised power n minus 1 x raised power n over n. So hint, uniform convergence of summation minus t raised power n on t on this close interval 0 to x, or x0 if x is less than 0, allows termwise integration. You have reconstruction from derivatives, talking about Taylor's formula now. So here, let x be cyclic we analytic at x naught. Prove that f of x is summation from n equals 0 to infinity of fn x naught over n factorial x minus x naught raised by n, and argue uniqueness of the power series. Hint, use Cauchy-Hadamard ratio test for the radius and coefficient formula an equals fn x naught over n factorial. Then you have the alternating error control. So find the minimal n so that the n term alternating approximation to log 2 is within 5 times 10 raised power minus 5. We did something like that before, right? So the hint is take log 2 to be summation for n greater than or equal to 1 for minus 1 raised power n minus 1, 1 over n, and require that 1 over n plus 1 is always less than or equal to 5 times 10 raised power minus 5. So that way now you have an error control. Then you have trigonometric addition from series. So you want to derive that sine x plus y is sine x cos y plus cos x and y. I mean, the derivation is possible. So using Cauchy products of the series for sine and cos. Hint, multiply the two series and collect odd and even powers. Appeal to uniqueness of coefficients. That's how that goes. Okay. Then we have quick reference here for radii and error tools. So we have radii of convergence classics here. So for exponential now, e raised power x is summation n greater than or equal to 0, x raised power n, n factorial, and the radius of convergence is 8. I mean, it's infinity. Same for sine, same for cos, like that, with different expressions. For logarithm, this is how it goes. For arctan, this is how it goes. For binomial, this is how it goes. So these are classic radii of convergence right there. Okay. So we have roots and ratio recipes now. I mean, we've seen this a lot. So for the root test, going by Cauchy-Hadamard, 1 over r is the limit of the supremum of n as n approaches infinity for the nth root of absolute value of an or cn or whatever the coefficient might be. All right. So ratio test, when the limit exists, you have r is limit as n approaches infinity of the absolute value of an over an plus 1. Then you have uniform convergence and compactor. We've talked about this a couple of times before now. So you have absolute value of x minus x naught less than or equal to r less than or equal to the radius of convergence bigger than summation from n equals 0 to infinity of an into x minus x naught raised by n is dominated by summation n greater than or equal to 0 of absolute value of an multiplied by rn. Hence, uniform convergence by the m-test on any compact k, which is a subset of x naught minus r, comma x naught plus r, like that. They have differentiation and integration rules also, which I think we've also seen a couple of times. So for absolute value of x minus x naught less than r, you have f of x equals summation over n greater than or equal to 0 for an into x minus x naught raised by n, which implies that f prime of x is summation from n greater than or equal to 1, n into an into x minus x naught raised by n minus 1. And then the integral is f of x dx equals c plus. I mean, we've seen this a couple of times. And then they have the same radius for both f and f prime and the antiderivative, that's the integral. Then you have Taylor error tools now. So for Taylor error tools, you have the Lagrange remainder, right? You have the Lagrange remainder. If the absolute value of f, the n plus 1 derivative of f evaluated at t is less than or equal to m between x and x naught, then the absolute value of Rn plus 1 of x is less than or equal to m over n plus 1 factorial into x minus x naught n plus 1. Then you have alternating series error for decreasing terms, which approaches 0. So absolute value of Rn is less than or equal to first omitted term. Then you have handy small x approximations with bounds, like that. Okay, so here, so you have e raised to power x now. That's approximately 1 plus x squared over 2. And the error is less than or equal to e raised to power absolute value of x over 3 factorial, absolute value of x raised to power 3. Then for sine x, you have x minus x cubed over 3 factorial. The next term boundary, now we have absolute value of x raised to power 5 over 5 factorial. For cos x, it's 1 minus x squared over 2. Next term bound is absolute value of x raised to power 4 over 4 factorial. Then for log 1 plus x, approximately x minus x squared over 2 for absolute value of x less than 1. Alternating bound, next is absolute value of x raised to power 3 over 3 if x is greater than 0 and small. Then you have series identities that you can trust, okay? So you have exponential addition, e raised to power x plus y is e raised to power x multiplied by e raised to power y. Then for Euler, e raised to power I theta is equal to cos theta plus I sin theta. We have trig additions from series or Cauchy product. So sin x plus y is sin x cos y plus cos x sin y. And then cos x plus y is cos x cos y minus sin x sin y. So these are some identities you can trust. Then there are boundary cautions now. Boundary cautions. So absolute value of x minus x naught is equal to the radius of convergence is case by case, because anytime you're at the boundary, you have to check for each point. Very important. And you can have absolute convergence inside, you can have divergence outside, or you can have boundary which may mix convergence and divergence pointwise. So typical examples will be log 1 plus x, which converges at x equals 1, but diverges at x equals minus 1, and arctan of x, which converges at x equals plus or minus 1, like that. And with this again, I mean, this video is more or less like, I mean, it looks somewhat like what we did in the previous video. So by the time you watch it, you should have an aggregated understanding of this whole idea of power series and elementary functions. So with this, I come to the end of this video. Let me know how helpful this is for you. If there's something you like on the trial, feel free to let me know. If you have subscribed already, thank you so much. If you haven't subscribed, of course, you want to go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you want to take it a step further. You want to, click on join and see the possibility of becoming a member of this channel. All right. So that gives you some special privileges like getting copies of some of the things I teach. And of course, we can even have one-on-one hangouts depending on your level of membership. right? Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. So, like, come your way again, keep doing maths right. Bye.